Okay, today we will be talking about the wave-particle duality. Now, we've already talked about the wave-particle duality with light. We just finished talking about Compton scattering. You might have noticed the homework didn't have any Compton scattering questions in it. That's because the homework site has no Compton scattering questions on it. But we had Compton scattering, we had the photoelectric effect, we had X-ray production, and like I said, there's one more, pair production, that are phenomena of light that can only be explained if light is behaving as a particle with a packet of energy that we call a photon of energy HF, constant times the frequency. But we also had things like the interference of light, and there were a number of others there that could only be explained with a wave nature of light, right? Polarization only could be explained with the wave nature of light. So we have two distinct natures, and it was decided that, as far as we can tell, they're both correct, and so we call it a wave-particle duality, that light is either a wave or a particle, and that brings some interesting ideas. Brings us to the quantum physics threshold. So here I'm starting the slide is showing what happens when you have photons pass through a double slit. When the photons pass individually through a double slit, so you have controlled light that's only allowing one photon at a time, it still builds up the interference pattern. Now, if you have one photon at a time and you build the interference pattern, you can only build the interference pattern if it goes through both slits. So it can't be a BB, because a BB can't go through both slits. It has to be a wave. The wave can go through both slits and then interfere with itself. But when you get to the detector is actually detecting photons. It's detecting particles. And so you have it acting as a wave when it goes through the slit, but acting as a particle when it gets to the detector. Now, if we look at this here is to set your mind in the appropriate direction as we go into quantum mechanics. So I have a couple quotes here. First from Niels Bohr. Anyone who has not been shocked by quantum mechanics has just not understood it, right? If you think, oh yeah, that makes sense, you clearly didn't understand it. This is Niels Bohr. It's not some pedestrian, It's somebody who was a fundamental person in the early days of development. Richard Feynman, the biography about Richard Feynman is entitled Genius. He is considered the last great physics genius. There was Isaac Newton, there was Albert Einstein, and there was Richard Feynman. And he says, I'm going to tell you what nature behaves like if you'll simply admit that maybe she does behave like this crazy, crazy stuff. You'll find her a delightful, entrancing thing. Richard Feynman was actually a very interesting man. He was a man that, you consider a Renaissance man. He liked to do all kinds of crazy things, not just study physics. For that reason, one of the guys I went to grad school with just didn't respect him, because how can you be a respectable physicist if you have interests outside of physics? The guy was a strange cat. True story. I was in the elevator with him, the chair of our physics department, and he was babbling on about something. The chair of the physics department turned to him and said, Cleon, someday I'm going to tell you what I really think of you. I don't think I've ever said anything so harsh to a person. Anyway, what's the point here? Quantum physics doesn't really make sense to most people. It only makes sense to people who have been completely indoctrinated in it and understand the nuances and are willing to accept that maybe material does these weird things that are nothing like what our experience tells us they do. So as we move into this, one of the first things about quantum mechanics, I told you, it's not specifically dealing with the small. It's just we only see its ramifications when we're dealing with the small. Quantum physics is a probabilistic thing. That means we're dealing with statistics and the likelihood of something occurring. Up to this point, we've treated physics as absolutely deterministic, right? If A happens, then B has to happen. I can just put an equation, boom, pops out what's going to happen. And when we have hard things like, thermodynamics, there's so many billions upon billions upon billions of particles that we can't possibly do the math to track them all. We still understand that if we could tell you exactly what's going to occur, right? We could predict the weather exactly right if we could track every molecule and every motion on Earth. But we don't have that ability, so we use statistics there. But quantum mechanics is not, we don't have the ability, so we use statistics. Quantum mechanics says that nature actually behaves probabilistically instead of deterministically. Einstein really rebelled at that idea. Remember, Einstein just named him as one of the three great geniuses here in physics. He has a famous quote, "I do not believe that God plays dice with the universe." What does that mean?
It's not random.
Yeah, he doesn't believe that the universe is random. Now, of course, Einstein's beliefs about God, depending on which quote you read, you might say he believed in God or did believe in God. But in this case, I'm pretty certain he's talking about nature when he says God. Right? We talk about Mother Nature. He's talking about nature when he says God. He believes that nature is not random. It's not you roll the dice and see what comes up. It's going to have to be determined. So he really rebelled against this idea. It doesn't mean he didn't work within the framework. He did a lot of work in quantum mechanics. It just did not make him happy because it just doesn't seem to make any sense that we can't know, we can't make predictions if we have enough knowledge. So we're dealing with probabilities, and of course probabilities are meaningless if you have only one object, right? If I have one die, I can tell you what the probability of each number coming up is. But if I roll it, I might find that I get 3 threes in a row. Probability of that was pretty small, but it's not a statistically significant sampling. When you get lots and lots of things like with thermodynamics, then it becomes very reliable. So we're going to deal with the probabilities in systems. And to start with that probability, we're going to go back to the double slit experiment, or single slit, doesn't matter how many slits. When we're doing an interference problem, we had the intensity variation. We developed equations that told us where we had the highest intensity and the lowest intensity for like a double slit. Or in the physics 252, we worked more carefully and got an equation to tell us the intensity at any angle for a single slit. So we can come up with these equations for the intensity, and in that derivation, physics 252 people, we used along the way the identity that the intensity is proportional to the electric field squared. Now, the electric field is what's fluctuating and what's actually carrying the information in the wave. The intensity is telling us where energy is being deposited. If we look at the particle nature, the photons are the units of energy. And so the intensity is telling us where photons are likely to hit. And so that intensity proportional to the electric field means that the electric field is giving us probability information about where the photons will be. It doesn't say the photon is here, it tells us the probability. So if we have enough photons, we'll see a pattern that fits the probabilities that we worked out. So here's two different ways of writing intensity. One is the number of photons per time and area times the energy of one photon. Right? So if I have 5 photons here, then I'm going to have energy of photon times 5 for my intensity per time area. Or I can look at as the probability of finding a photon in a given area for a given time. Two different ways of talking about it. The second one had probability in it. So because intensity was proportional to the electric field squared, and the intensity tells me the probability of finding a photon, then that means the probability of finding a photon is proportional to the electric field squared. I go through all of this, we're not doing light here, but to set up that the electric field is actually a function of position and time. We call it a wave function. It's a function that describes a wave. And the probability of finding the particle at any location is proportional to that electric field, the wave function squared. That idea is exactly what we do in quantum mechanics. So in quantum mechanics, I got to go to a question here before I go to what we do in quantum mechanics. What aspect of the electric field gives the probability of finding a photon at a given location? This would be, can you remember from 10 seconds ago? There we go. Okay, so I clearly was not doing a good job of making this clear because we do not have a very clear description. So let's just go to what did I say? So Aaron, what did I say?
You said that it was proportional to the square of the electric field.
Okay, that is correct. That's what I said. So the probability was the same as the intensity, proportional to the electric field squared. Now the electric field squared, this is what, things broke down because I think I didn't make it clear. The wave function for the electric field is some function of x and t, and it's equal to the amplitude times cosine of, that's like the most complete. So it's amplitude times the cosine of this stuff. And so if I take this equation and I square it, and I take the time average, what's the time average of cosine squared? The time average of cosine is 0, right? So it spends as much time above and below. But if I take cosine squared, it's going between 0 and 1. And its average is halfway in between. So it's actually 1/2. And so the average of this is going to be 1/2. And so the amplitude squared is what's going to tell us the probability of the electric field being someplace, or of the photon being somewhere. So that's how the electric field squared comes into the square of the amplitude. Notice frequency was inherent in this equation. Omega is the angular frequency. But over time, that's going to average to 0. Or not to 0, it's going to average out, though, over time. Okay, now getting back on track. Okay, so 1923, Louis de Broglie said, well, we saw that for light has a momentum of P is equal to H over lambda. That was P is equal to the energy of the photon divided by the speed of the photon. That was what we understand. That is still what we understand for the momentum of a photon. And I told you about the experiment that didn't work, it spun backward. It was because they had some air in there. If they completely evacuate the tube, it does work the way theory predicted. It does rotate in the direction predicted by twice the change of momentum when you reflect compared to when you absorb. So Louis de Broglie said that equation should apply to other things. So I should be able to take something like an electron. And if electron has a momentum, P equals mv, I'll put the gamma in here just to be relativistically correct. If I put that in here, that should tell me the wavelength for any particle. Because particles, what's special about a photon? Why can't an electron have a wavelength? Why can't Jerry have a wavelength? Now, if we were to calculate Jerry's wavelength, according to de Broglie. What's the momentum of Jerry if he's running as fast as he can? Jerry's got an inflated sense of his speed, but he can probably run somewhere around, let's say, 5 meters per second. And he has a mass, this is too high, but let's say he has a mass of 100 kilograms to make life easy. So 100 times 5, 500 kilogram meters per second. Right? And if he's walking, it'll be like 100 kilogram meters per second. So somewhere in the 100 kilogram meters per second range is his momentum. What is Planck's constant? So I'm going to take 662 just to make it really easy to do the math. He's now flying. He's going very fast. So if I take that, what would his wavelength be? Would you consider that a long or a short wavelength? That's an extremely short wavelength. So you know what? If we're looking for Jerry's effects, like we send Jerry through a single slit, we have him running through the door. Right? That works. He runs through that door. He should be diffracted if he's a wave. Agreed? And so we should have, well, this one, it's A sine theta is equal to m lambda for the first minima. Take the first minima on each side, and we'll say Jerry's between those two minima, right? I mean, this is a realistic calculation. It's one that we actually do, except for we don't apply it to Jerry for the reason that's obvious right here. Theta is clearly going to be a small angle, so I can use a small angle approximation. Let's say that door is 1 meter in diameter. What's the angle that Jerry's going to be diffracted? 10 to the minus 36 radians. And so the width of the diffraction for Jerry is going to be, you have to go way outside of the solar system before you can even tell that Jerry's widened a little bit. So it's useless to talk about quantum physics applying to Jerry, Jerry having a wave nature, because he's so massive that we don't see the effect. So this is only going to be useful to us with small mass items. What's our smallest of small mass items? The electron. So we generally apply this only to electrons. That is, for general physics or college physics, we only apply it to electrons. For higher levels, yeah, we do more. But de Broglie says, okay, so Jerry should have a wavelength and I should be able to do wave things with it. So then we have things like the famous Davison-Germer experiment where instead of shining X-rays on a crystal and looking at diffraction caused by the repeatable positions of the atoms, say, let me shoot electrons at it and see what happens. Well, they. And what they found was, sure enough, you had scattering. And if you use de Broglie's projected equation for the wavelength of an electron based on its momentum, the scattering angle matched what it would be if it was light with that wavelength. And so there was an experiment that said, hey, the electrons scatter like they have a wave. Like de Broglie was right, that electrons have both a wave nature and a particle nature. That's what I just said. Thomson did it with some crushed powders. It's basically the same idea, so I'm just going to skip right over that. Pattern diffraction pattern is what that was. So then Erwin Schrödinger gets into the mix, and he says, well, if, in fact, electrons are behaving like waves, then I should be able to make a wave equation that I can use to find the wave function. And as I said to the people on Tuesday, everybody said, if you're so smart, what is it? And so we sat down and he figured out a wave equation, an equation we can use to find what the wave function is, which is equivalent to the electric field for light, the function that gives us, we call it the probability density. If we square that probability density, if we square the wave function, then it'll tell us the probability of the particle being in a certain location. So next, an obvious experiment is, experiments showed that if you shot single photons at a double slit, you would build up a diffraction pattern. What happens if I shoot single electrons at a slit? Right? Our brains say it's fine, light's a wave, waves will go through both slits. But our brains tell us electrons are still particles. I don't care what the teacher's saying. I know an electron's a particle. How many people can agree with that? The research is pretty strong that students will learn to parrot back what we teach them in physics, but they don't necessarily believe it. They say, yeah, the teacher says this, so I have to answer this. But really, the electron's a particle. Well, experiments shooting electrons through double slits, if you just shoot a few electrons one at a time, you see a picture like the top one. That's only 40 electrons. It's not very statistically significant, but you can kind of see a pattern, right? You get up to 200 and you see a strong pattern. You get up to 2,000, well, that's pretty undeniable. And if you get a significant number of electrons going one at a time, you get a pattern that shows intensities that match exactly what you would have had for light of that wavelength using the de Broglie wavelength. So we talk about matter waves. That is a wave function to describe matter, a wave function to describe an electron. Here is a very practical example of the wave nature of electrons. You guys have probably, no one here has ever used an electron microscope, right? It'd be pretty rare since we don't own any here at Union College. In graduate school, I had to use a scanning electron microscope. The electron microscope is shooting electrons, high energy electrons, at your sample. And then those electrons, because they have a wave nature, you can use them to actually image the sample. And so in my case, I was putting things like sodium chloride crystals or magnesium oxide crystals that I damaged with the laser, and I want to see what kind of damage my laser has done to the surface. For it to work, you actually have to coat it with something that's conductive. Since gold will make very thin films, we just coat them with gold, which, you know, I suppose I could have tried to pocket some of that gold and had a nickel's worth of gold, but it's behaving like waves, and we can focus those waves. Now, you don't focus them using a traditional lens. You focus them with coils. You're making a magnetic field, and when the particles are going through that magnetic field, you have a force that's force equal to QV cross B, definitely treated as a particle there, but that's what's used to actually focus the electron beam. So it's an example of using the wave particles of the electrons in a device to see something. Why would you use electrons rather than light? I mean, there has to be a reason, not just because I can. What's a weakness of using a microscope? Remember, we learned about diffraction, light bending around edges. And so we had that Rayleigh criterion for our resolution. The smallest thing we could resolve was where we had the first minimum overlapping with the peak. And so our resolution was equal to the radius of the aperture times, okay, I said that wrong. The equation was A sine theta equals 1.22 lambda for the first minimum. And from that, we found what the resolution limit was. But the problem is we have this limit of resolution that's proportional to the wavelength. The shorter the wavelength, the smaller the detail we can see. Well, what's the shortest wavelength we can get with visible light? About 400 nanometers. So if you want high resolution microscopes, it's a visual microscope, you use something like blue light because it has shorter wavelengths that gives you better resolution. But with the electron microscope, we can control the wavelength by just adjusting the momentum of the electron. And we can choose wavelengths that are much shorter than what we could get with even X-rays. And so that gives us much better resolution possible with an electron microscope. Okay, back to Louis de Broglie. What was the key of his hypothesis? Notice every statement here is a true statement. It's what was the key for de Broglie's hypothesis. All right. We had some shifting around. It was better, then it got worse again. Whoops. I assume the others are 0. I can't see. You could read them. I can add 12, 16, 17. Actually, there are 2 more somewhere down here. I can't read what the bottom 2 are. Someone want to tell me what the bottom 2 numbers are? 0, 2? Okay. So we did not have complete agreement here. Let me just have James. First, what was de Broglie, the equation to go with de Broglie's hypothesis, and then what was it all about?
Wasn't it lambda equals over p?
Yes. And what was the point then?
He's saying that for particles other than photons, you can also relate the momentum and wavelength in the same way as you do for photons.
Okay. So the key there was that they have a wave nature. Right? Electrons can carry momentum. Of course they can. They have a mass. You give them a velocity, they have momentum. Electrons can scatter. Yes. The electrons can scatter was actually, we explained the scatter by its wavelength, but you can have a billiard ball scatter off of something as well. So a particle could scatter. That wasn't a key part of this. Photons carry momentum. Yes, but that was relativity. That wasn't de Broglie. Photons can scatter. Yeah. Go back to Rayleigh and me scattering. Photons have a particle and a wave nature. That's what led de Broglie to his hypothesis that so should other things like electrons. Now, I said that Erwin Schrödinger came up with a wave equation, something to help us find the wave function. At the same time, Werner Heisenberg was working on quantum physics, and we're going to talk about the models for an electron models for an atom next week. And one of the things that people realized was we simply have no idea where electrons are in atoms. We can't tell what they're doing. And so they said, well, how are we going to deal with that? Schrödinger came up with the wave equation to find a wave function to try to describe the probabilities of where you're going to find the electrons and the properties of the electrons. Werner Heisenberg said, we can't find it, so forget about it. Let's just look at what we can do. Let's start classifying. We have these properties, the magnetic moment, otherwise known as the spin. We have the momentum, and take the properties that we can identify and start trying to classify them. And so he started making a bunch of matrices. He just thought he was making tables, passed it off to his advisor, who said, I don't know what to do with this math. Well, he sent it to a mathematician friend. And the mathematician friend said, oh, hey, yeah, I see you started working on group theory. Well, we have we? And so the mathematician helped them to develop a matrix method of classifying the properties. And it turns out that you get the same results about what's going on with electrons, whether you use the matrix method of Heisenberg or the wave method of Schrödinger. But Heisenberg also came up with a very important relationship that's called the Heisenberg uncertainty relationship, or Heisenberg uncertainty principle, it says here. The Heisenberg uncertainty principle says that the absolute fundamental nature of matter is such that for any particle, I'm always going to have some uncertainty in its position and some uncertainty in its momentum. But there's a relationship between those two. The better I know the momentum, the worse I know the position, and vice versa. And so he came up with a mathematically derived relationship that we call the uncertainty relation. This is actually something that's not beyond the realm of our Physics 252 students of deriving. That says the product of your uncertainty in position multiplied by your uncertainty in momentum is always greater than or equal to 1/2 of Planck's reduced constant, 1/2 of h divided by 2 pi. So we introduce a new constant here. H bar is equal to h over 2 pi, which turns out it's like 1.058 times 10 to the minus 34 or something like that. We use that over and over and over in quantum mechanics. And so this uncertainty in position multiplied by the uncertainty in momentum is always going to be greater than or equal to that. Fundamental. That's not because of our inability to measure. It's because that's the nature of matter. So it leads you to those funny jokes. What is it? Schrodinger and Heisenberg, and I can't remember the other one. I can't tell the joke if I can't remember the third person. Are driving in a car, and the policeman pulls them over, and he tells Heisenberg, "Do you know how fast you're going?" Heisenberg says, "I have no idea, but I know exactly where I am." And the policeman says, "You were going 50 miles an hour." Heisenberg gets angry and says, "Now I'm completely lost." Okay, why is that joke worth at least some kind of groaning laugh?
You have to trade off between.
Yeah, he knew exactly where he was, which according to this relationship means if your uncertainty in position is 0, your uncertainty in momentum is going to have to be infinite. 0 pi infinite times infinity is indeterminate, so it still can work. So that's why he had no idea what his speed was, his momentum, because he knew exactly where he was. But then when the policeman told him exactly how fast he was traveling, of course, you have to suspend your, he was stopped at the time the policeman was talking to him. But if he knows exactly how fast he was traveling, then he has no idea of his position by that same equation. And so then the policeman goes, after he gets upset, he goes and he pops open the trunk, and he sees a dead cat in the trunk, and he says, "Did you know there's a dead cat in your trunk?" And then Schrodinger gets angry and says, "Well, I do now." Anybody know why that is even a joke? Schrodinger's cat. So let me explain Schrodinger's cat, because that's another important thought experiment. Very key that it's a thought experiment, okay? Don't try this at home. To understand the probabilistic nature of quantum mechanics. So here's what the Schrodinger's cat, quote, experiment, end quote, is. You have an atom that is radioactive. Now, according to quantum physics, this radioactive atom has a wave function that as a function of time is equal to a e to the minus at plus b times 1 minus e to the minus at. What those states are is A is that the atom is undecayed. B is that the atom has decayed. And we call this a superposition state. That is, at any time, there's a certain percentage, in this case it's e to the minus at, that the atom has not yet decayed. And there is the corresponding percentage that the atom has decayed. And so quantum physics, we call this a superposition state. At any moment in time, that atom is in both states A, undecayed, and state B, decayed. And it's just a bigger proportion in one state than the other. And then according to quantum physics, if I check the state, it will go to being 100% one or 100% the other. So when I check it, I reset my system. So if I check and I say, oh, the atom hasn't decayed yet, then it's back to 100% undecayed, and we start over. If I check and it's decayed, now it's 100% decayed, and the experiment's done. So that seems kind of random, doesn't it? That it can be simultaneously in two states, decayed and undecayed at the same time. And so Schrodinger said, well, let's give ourselves an example. Here's a box, and in this box, we put Fluffy. Okay, this is Fluffy the cat. Okay, just deal with it. Then we put our little radioactive sample, which is described by this wave equation. And around that sample, we're going to put a detector that's going to, with 100% efficiency, because we're building an imaginary experiment, with 100% efficiency, it will detect the radiation when that atom decays. And when it detects that radiation, it's going to drop the hammer. And what do we have sitting under the hammer but a vial of cyanide? So here's the situation. When the atom decays, the hammer drops, it breaks the cyanide. The cyanide then fills the cage, the cat breathes it in, the cat dies. Understand? I assume cyanide's a gas, right? All I can think about is, Jim Jones, they put cyanide in their Kool-Aid. So they put a poison anyway that's going to kill the cat. So the idea is you put the cat in here, you close the cage. As long as you don't look at the cage, you're going through this function. The cat's states can be described as A is now alive for the cat and B is dead for the cat. And so after one half-life, the time when it's 50% probability of it decaying, you would have the cat is simultaneously 50% perfectly healthy and 50% dead as a doornail. That's what quantum physics says. And when does the cat die according to quantum physics? Only when you check. If you look at the cat, it'll either be fully alive or fully dead. If it's fully alive, you start over your time. If it's fully dead, you're done. And so that's why that joke is a joke, because you've got the Schrodinger's cat experiment going on in the trunk, and the policeman checks and now killed the cat because the cat might have been 0.001% fully healthy until the policeman checked. And now it's dead. Goes back to those quotes at the beginning about, Feynman. If you'll accept that reality is doing this weird things, you'll find it interesting. So I used Heisenberg's uncertainty and a joke to lead me into that. Now, it's interesting to look at a little bit about Werner Heisenberg. He was one of the brilliant physicists, but he had what I would consider a fundamental flaw. During World War II, he stayed in Germany and led their project to build the atomic bomb. How many people knew that Germany was building an atomic bomb? Okay, a fair amount. Americans actually theorized that the Germans were building an atomic bomb because the Germans suddenly stopped sharing information. Even during wartime, the scientists were still communicating, right? We're all above all that political stuff, right? Look down our noses at it. All of a sudden, the Germans stopped communicating about their nuclear research, and they started collecting nuclear materials, and the American scientists said, ooh, they could be using this to make something bad. And so they wrote a letter. They had Albert Einstein be the signatory, the person who signed it, gave it to the president saying, the Germans could very well be building this bomb that could destroy life on Earth, or at least us, and, America would cease to exist. And so that started the Manhattan Project, Americans building a nuclear bomb. Did we build a nuclear bomb? Yes, we did. Did Germany build a nuclear bomb? No, they didn't. They actually stopped the process. It's believed it was largely because of racism, that there were Jewish scientists who were leading out in the project, and Hitler couldn't deal with that. Didn't trust them. And so in the end, we were the only ones that developed the nuclear bomb. We're the only ones who have ever used a nuclear bomb in war. We'll talk about that later. I consider this not a happy thing. Just to make sure we're clear on that. So how can Heisenberg come with this uncertainty relation? We can think of light again. Light has a momentum of P is equal to h over wavelength, right? Now, if you have light that is continuous like this, you know exactly what the wavelength is. So you know what so you know the momentum exactly, because you know exactly the wavelength. But what's the position for this wave? Where is it located? No one knows, right? It could be anywhere. Because you have this light that extends forever, you don't have a way to define a position. Your uncertainty position there is infinite, but your uncertainty in the momentum is zero. Now, if we're going to identify the position of light, we have to send a packet of light, a burst. So here we have two wave packets. You have a flat line on what's not shown. So you have flat line like that. If you look at the first one, you would say, okay, its position is somewhere between there, let's say. And so I can say my uncertainty in position has to do with that width. But here's the thing. How do you make a packet like that? Some of you have taken calculus and you've learned about Fourier transforms. And the whole idea of Fourier transforms is that you can describe any wave as an infinite collection of sinusoidal waves. So you have a whole bunch of different wavelengths. And the smaller the packet, the broader the range of wavelengths you have to use to make that packet, which means your uncertainty momentum is getting larger as the packet gets smaller. And so for these, your uncertainty in position, this is fairly small, but the uncertainty in momentum is large because you have to have lots of different wavelengths to make that packet. This one here has a bigger uncertainty in position, but the uncertainty in momentum is smaller because to make the bigger packet, you don't have to have as many wavelengths. It doesn't have to have as big a spread. And so what Heisenberg did is he found that using a Gaussian distribution for the wave packet gave you and it can actually be proven that it's the optimum relationship between the spread in the wavelength and the spread in the position. And so by analyzing Gaussian packets, he was able to come to this relationship that for a Gaussian packet, that's an equal sign. And for anything that's not a Gaussian packet, it's going to be bigger than that. So it was by treating the wave nature and the fact that the momentum has to do with the wavelength range that he was able to come up with that. So it's a theoretical construct, as far as we know, is correct, and it just describes the fundamental nature of matter, that you can't know identically the position and momentum. Now, once again, going back to Jerry. We talked about Jerry's wavelength. And so we could take Jerry's wavelength and go back to where we started his momentum. And using that relationship, Jerry's momentum is on the order of 100 kilogram meters per second squared. How big is his uncertainty for the minimum uncertainty possible? Let's say that his uncertainty momentum is, it's 100 kilogram meters per second, the uncertainty is about 5 kilogram meters per second squared, or per second squared. If it's about 5 kilogram meters per second for his uncertainty position, then what's his uncertainty momentum going to be like? Let's write this out, because I get the feeling people are kind of looking at me saying, I'm not sure what you're talking about, sir. delta P is about 5 kilogram meters per second. So that means delta X is greater than or equal to 10 to the minus 34 divided by 10. His uncertainty in position, according to the Heisenberg uncertainty relation, is about 10 to the minus 35 meters. Who can measure 10 to the minus 35 meters? No one, right? So we don't look at Jerry and say, I'm not exactly sure where he is because he's, I'm not sure of his momentum going to have this relationship. Because Planck's constant is really small. Now, I mentioned this before. If you go look at George Gamoff's books, he has books that explain what would happen in weird situations. So what if Planck's constant, instead of being 10 to the minus 34, was something like 10? If Planck's constant was on the order of 10, then for the same uncertainty momentum, Jerry's uncertainty in position would be about a meter. So I'd be he's somewhere between here and here, but I can't tell where. It says he's exactly there. So if Planck's constant was large, this uncertainty relation would be very real to us. And it wouldn't seem bizarre and crazy because it'd be what we experience. But because Planck's constant is so small, that uncertainty is not something we experience in our lives, and thus it seems bizarre. So you have fun things like, if you parked your car in the garage and Planck's constant was like 10, you'd be afraid to walk into the garage. Why? Parked in the garage is plus or minus a couple feet for its position, right? You just know it's in the garage. Yeah, your uncertainty momentum is going to be on the order of, 20, 30, whatever kilogram meters per second. You can step in the garage and get run over by that car. Right? It's a very different world when we start talking about quantum physics. It's not just the simple, sensical world that we've learned to love, I hope. Okay. This here is actually going through doing a calculation with the uncertainty principle. If we have electrons that go through a slit, I have an uncertainty in their y position, notice the y is defined, that is the size of the slit. And using the Heisenberg uncertainty relation, I can take that uncertainty in their y position and relate that to an uncertainty in the momentum in that direction. So in this, we would say that momentum in the y direction we believe is 0, right? Because it shows it as horizontal motion. But we have uncertainty momentum in the y direction is h bar over 2 delta y. Now here's something I should have pointed out. In that relationship, uncertainty in position times uncertainty in momentum is uncertainty in momentum in the same direction as the uncertainty in the position. So that's why I'm only using y subscripts here. And so then we have the light going through that slit could have px and a maximum deviation of delta py. And so we can get a spread that we see from this equation with just using the uncertainty relation. And so that's what the problem here is. The y coordinates is passed through the slit going between plus and minus a over 2. And so we have an uncertainty in the y position that's 1/2 of the slit width. Right? We're saying it's at the middle, plus or minus half the slit width. And going through that, what's the y component of the momentum of an electron that leaves the slit in angle theta? Well, you just use your trigonometric equations. I'm out of time. Most electrons fall within the central maximum that you get through this.